BioniChaos.com is a platform dedicated to the development of innovative biomedical data tools with a focus on interactivity, gamification, and accessibility. The website hosts a variety of web applications designed for exploring and visualizing complex biomedical data, making these tools accessible to both researchers and the general public. The EEG Seizure Detection Project is one such tool, providing users with an interactive platform to explore EEG datasets, visualize seizure events, and understand machine learning models applied to epilepsy detection. This tool serves as a resource for both educational purposes and research, enabling users to delve into the nuances of EEG data and replicate findings related to seizure detection. Future developments aim to enhance the interactivity of the tool, allowing for deeper data exploration and the integration of real-time analysis features. The dataset used in this web application is focused on detecting epileptic seizures from EEG signals, which are converted into 2D rhythmicity spectrograms. This process involves transforming 1D EEG signals into visual images through a short-time Fourier transform, allowing for the analysis of frequency components over time. The dataset consists of images classified as either seizure or non-seizure, which are then used to train a convolutional neural network, CNN, for automated seizure detection. The research highlights the importance of developing such automated systems to aid in the early diagnosis and treatment of epilepsy, which is a significant neurological disorder globally. Incorporating this dataset into an interactive web application allows users to explore the underlying data, visualize the spectrograms, and replicate the seizure detection results. This could be particularly useful for educational purposes, as well as for further research in the field of EEG analysis and machine learning applications in healthcare. The original dataset can be accessed on Zenodo, EEG Seizure and Non-Seizure Image Dataset, pate/zenodo./record 6055011. The study associated with this dataset is detailed in the paper Epileptic Seizure Detection Using Rhythmicity Spectrogram and Cross-Patient Test Set, which emphasizes the effectiveness of the CNN model in classifying seizure and non-seizure images, achieving a test set accuracy of up to 61%. The dataset and study support ongoing research into more accurate and efficient methods for seizure detection, with potential future directions, including the integration of additional EEG channels, exploring other deep learning architectures, and enhancing the dataset with more diverse patient data. You can review the full dataset description and methodology in the attached paper and image file for a comprehensive understanding of the research work and its applications. To proceed with the development of your web application, consider the following steps. 1. Enhance user interaction. Implement interactive features that allow users to dynamically explore the EEG data. This could include features like zooming in on spectrograms, overlaying multiple spectrograms for comparison, and providing real-time filtering options, e.g., selecting specific frequency ranges. 2. Add annotations. Allow users to add annotations or notes to specific EEG images. This would be useful for educational purposes or for collaborative research, where different users can share insights directly on the platform. 3. Integrate machine learning models. If possible, integrate pre-trained models or offer options to upload custom models for classifying new EEG data. Provide visual feedback on how the models perform with the provided dataset. 4. Data visualization dashboard. Develop a dashboard that presents key metrics and statistics about the dataset, such as the distribution of seizure versus non-seizure images, model performance metrics, and time series analysis of the EEG signals. 5. User tutorials and documentation. Add a section for tutorials and documentation to guide users through the different functionalities of the web application. This would help users unfamiliar with EEG data or machine learning to get the most out of the application. 6. Replication of study results. Include a step-by-step guide or automated script that allows users to replicate the results from the original study. This could be done by integrating Jupyter Notebooks within the web application or providing downloadable scripts. 7. Customization and scalability. Ensure that the web application is easily customizable and scalable. allowing users to upload their own datasets and models in the future. This could turn your application into a more general tool for EEG data analysis. 8. Optimization and performance tuning. Finally, as the application grows in complexity, focus on optimizing performance, particularly when handling large datasets or running complex models directly in the browser using tools like TensorFlow.js. These steps would help you transform the web application into a comprehensive tool for both research and educational purposes in the field of EEG analysis and seizure detection. To expand on the concept of a data visualization dashboard, consider designing a dynamic and interactive interface that centralizes all critical data insights related to the EEG seizure dataset. This dashboard would feature a variety of visualizations that allow users to explore and understand the dataset deeply. For instance, you could include real-time graphs that display the distribution of seizure versus non-seizure events across different subjects and conditions. Users could interact with these graphs to filter data by parameters like time, frequency, or patient characteristics. Moreover, the dashboard could offer a detailed analysis of the model's performance metrics, such as accuracy, precision, and recall, visualized through RC curves and confusion matrices. By allowing users to drill down into these metrics, the dashboard could help identify specific areas where the model excels or struggles, thus guiding further research or model refinement. Incorporating time series visualizations would also be essential, particularly for EEG data, which is inherently temporal. These visualizations could provide insights into how seizure patterns evolve over time and how they correlate with other physiological signals. Users could explore these patterns through interactive timelines, zooming in on specific episodes for a more detailed view. Finally, the dashboard should be designed with customization in mind, allowing users to create and save their own views, which they can return to for ongoing analysis. This would not only make the dashboard more user-friendly, but also transform it into a powerful tool for both researchers and clinicians who need to analyze EEG data quickly and effectively. The generic model used in the EEG seizure detection project achieved an average training accuracy of 91.89%, validation accuracy of 88.17%, and test set accuracy of 61%. These figures highlight the model's robustness during training and validation phases, but also indicate room for improvement in its generalization ability on unseen test data. This discrepancy suggests potential areas for further research and refinement, particularly in enhancing the model's performance on new datasets, which is crucial for reliable real world applications of seizure detection in EEG analysis. The structure of the data is organized into different folders, each representing a different stage of the dataset: train, test, and validation. Inside each of these folders, the data is further divided into two categories: seizure and non-seizure. Each category contains a set of images, which are individual frames of EEG spectrograms corresponding to either seizure or non-seizure events. This structure is common in machine learning datasets used for training and evaluating models, where data is split into different subsets to train the model, validate its performance during training, and test its generalization ability on unseen data. The explanation of the dataset structure and the purpose of the images is likely derived from the research paper and dataset documentation that you are working with. The paper provides context on how the EEG data was preprocessed and converted into spectrograms, and how these images are used in machine learning models for seizure detection. If you are looking for a more detailed explanation, it would be best to consult the research paper associated with the dataset or any accompanying documentation, such as the copy of the published paper.pdf in your data folder. These sources would provide the necessary details on how the dataset was constructed and how the images were generated and used in the study. Overview of the dataset and research. The dataset in question is derived from the CHB MIT SCALP EEG database, which contains EEG recordings from pediatric patients with intractable seizures. This specific dataset focuses on patients CHB01, CHB02, CHB03, and CHB05, converting their multi-channel EEG signals into rhythmicity spectrograms using short-time Fourier transform, STFT. The spectrograms serve as input for a generic convolutional neural network, CNN, to classify seizure and non-seizure events. The CNN model achieved an average accuracy of 91.89% on the training set, 88.17% on the validation set, and 61% on the test set. Summary of BioniChaos.com. BioniChaos.com is an innovative platform that merges biomedical data science with interactive web applications. It focuses on providing educational and practical tools for visualizing and analyzing complex biomedical datasets. The platform hosts a range of tools designed for both researchers and enthusiasts, emphasizing gamification and user engagement. By integrating real-time data visualization and interactive elements, BioniChaos.com aims to make biomedical data accessible and engaging for a broad audience. Introduction to the EEG Seizure Detection Tool. The EEG Seizure Detection Tool on BioniChaos.com is a specialized web application that allows users to explore, visualize, and analyze EEG data, particularly for detecting epileptic seizures. This tool leverages advanced machine learning techniques, including convolutional neural networks, CNNs, to classify seizure and non-seizure events based on EEG spectrograms. Users can interact with the dataset, visualize the spectrograms, and replicate the research findings, making it a valuable resource for both educational and research purposes. Data structure explanation. The dataset is organized into three main subsets: train, test, and val, each containing two categories: seizure and non-seizure. The images within these categories are spectrograms derived from EEG recordings, representing either seizure or non-seizure events. The structure facilitates training, validation, and testing of machine learning models. The explanation of this structure is based on both the research paper you provided and the data organization itself, which is standard for machine learning tasks in the biomedical domain. This structured organization ensures that the models can be effectively trained and evaluated, with clear distinctions between the data used for learning and the data used for validation and testing. This approach also helps in maintaining the integrity of the model evaluation process, providing insights into how well the model generalizes to unseen data. If you're interested in the full details, the research paper and dataset documentation offer a comprehensive explanation of how the data was processed and utilized in the study. This ensures that users can fully understand the methodology and apply it to similar research or educational projects. The structure you've provided outlines a directory with various files and subdirectories, particularly focused on EEG seizure and non-seizure image datasets. Here's how the structure is organized. 1. Main directory, data, contains a PDF, copy of the published paper.pdf, and an image, dataset details.png. The key content is within the EEG seizure and non-seizure image dataset directory. 2. EEG seizure and non-seizure image dataset. This directory holds another folder named Dataset, which is further divided into test, train, and val subdirectories. 3. Subdirectories, test, train, and val. Each of these contains further subfolders named non-seizure and seizure. Within these subfolders are numerous .png files representing images of EEG data, categorized by whether they are from seizure or non-seizure events. Selecting files for display. If your web application is focused on displaying specific EEG data, you would typically start by selecting images from either the seizure or non-seizure subdirectories within the test, train, or val folders, depending on the dataset split you are interested in, e.g., testing, training, or validation. For example, seizure images. If the application is to highlight seizure events, you could start by displaying images from the seizure subfolder within the test directory. Non-seizure images. Conversely, if you're interested in normal EEG patterns, start with images from the non-seizure subfolder. For instance, you could display 10.png from the seizure folder under the test subdirectory. Folder navigation. First selection. Choose either test, train, or val based on your need, e.g. displaying test data. Second selection. Within the selected directory, choose seizure or non-seizure, depending on the type of images you want to display. Final selection. Pick specific images like 10.png for seizure events or 137.png for non-seizure events. This approach ensures the web application accurately reflects the specific EEG data type you're focused on. The presence of a file named 10.png in both the seizure and non-seizure folders might indicate a few possibilities. 1. Accidental duplication. The file could have been mistakenly copied into both folders during data preparation. 2. Mislabeling. The file might be incorrectly categorized as both a seizure and non-seizure image due to a labeling error. 3. Versioning issue. Different versions of the dataset might have resulted in the same file name being used in different contexts. To address this, it's important to carefully review the contents of both files. If they are identical, you may need to correct the labeling. If they are different, but share the same name, consider renaming one of the files to avoid confusion. The val folder within your dataset likely stands for validation. In machine learning, datasets are often split into training, validation, and test sets. The training set is used to train the model. The validation set is used to tune the model's hyperparameters and assess its performance during training. And the test set is used to evaluate the model's performance after it has been fully trained. The images in the val folder would be used during the training process to validate the model's performance, helping to prevent overfitting. In a dataset like yours, where images are categorized into seizure and non-seizure folders, having the same file name in both categories might indicate a few possibilities. 1. File duplication error. The file 10.png might have been accidentally copied or incorrectly labeled, leading to its presence in both folders. 2. Different contexts. The images could represent different aspects of similar data, e.g., a specific time frame where one shows a seizure and the other doesn't, but were named the same by mistake. 3. Dataset versioning. If the dataset went through revisions, some files might have been relocated or reclassified without renaming them. It's worth manually checking the content of both files to determine if they are indeed duplicates or if they contain different data that was misclassified. Dataset overview. The dataset consists of EEG recordings from patients with epilepsy, categorized into seizure and non-seizure segments. These segments have been processed into rhythmicity spectrograms, providing a visual representation of the EEG data. The dataset is organized into three primary folders: train, test, and val, each containing further subfolders for seizure and non-seizure images. Enhancing the web application. To make the web application more engaging and useful for replicating the results in the paper, consider the following developments. 1. Interactive data exploration. Implement functionality to load and visualize different spectrograms dynamically based on user input. You can add drop-down menus or search bars to allow users to explore specific patients or conditions, seizure versus non-seizure. Enable users to compare spectrograms side by side, adding annotations or notes to highlight key differences between seizure and non-seizure data. 2. Machine learning integration. Incorporate machine learning models directly into the web application to allow users to run real-time predictions on the EEG data. This could involve pre-trained models that predict seizure occurrence or allow users to train models on subsets of the data. Visualize the decision boundaries of the model using interactive plots such as raw C-curves to provide insights into model performance. 3. Reproducing paper results. Create a dedicated section for replicating the experiments discussed in the paper. Provide step-by-step instructions and pre-configured settings to allow users to run the same analyses and compare their results with the published findings. Include interactive Jupyter notebooks embedded within the web application to guide users through the data analysis process, allowing them to tweak parameters and see the effects in real time. 4. Educational content. Add educational resources to explain the concepts behind EEG, spectrograms, and machine learning in the context of seizure detection. This could be in the form of videos, articles, or interactive modules. Offer quizzes or interactive exercises that test users' understanding of the material and provide immediate feedback. 5. User contributions. Enable a feature where users can upload their EEG data, visualize it, and run the same analysis pipeline used for the provided dataset. This can help in broadening the application's utility for different types of EEG data. Consider adding a community section where users can share their results, insights, or custom models, fostering collaboration and knowledge exchange. 6. Real-time analysis. Integrate real-time EEG data streaming and analysis. If possible, allow users to connect their EEG devices, visualize the data in real time, and apply the machine learning models for instant feedback. These enhancements would not only make the web application more engaging, but also turn it into a comprehensive tool for both education and research, allowing users to interact deeply with the dataset and replicate the paper's findings effectively. Expanding the features of your EEG seizure detection web application can make it more engaging and informative for users. Here are some ideas to consider. 1. Real-time data analysis. Implement real-time data analysis features where users can upload their EEG data and get instant feedback or predictions about seizure activity. This would involve integrating machine learning models that can process and analyze EEG data on the fly. 2. User annotations and labels. Allow users to annotate the spectrograms with their own labels, possibly indicating areas where they suspect seizure activity. These annotations can be stored locally or sent to a server for further analysis. This could turn the application into a valuable tool for collaborative research. 3. Interactive visualizations. Enhance the visual experience by allowing users to manipulate the spectrograms, such as zooming in on specific sections or adjusting the time window of the EEG signals displayed. You could also add overlays to highlight different frequency bands or features that are relevant to seizure detection. Educational resources. Add educational content to help users understand the basics of EEG and seizure detection. This could include tutorials, video explanations, and interactive quizzes. Providing insights into the underlying principles of EEG analysis and how seizures are detected can make the application more than just a tool. It can become a learning platform. 5. Integration with external tools. Consider integrating your web application with other tools and platforms. For example, you could enable the export of data and annotations to formats compatible with popular EEG analysis software. Alternatively, you could connect the app with cloud-based services that offer more advanced data processing capabilities. 6. User-friendly interface. Continue improving the user interface to make it intuitive and accessible. Features like a guided tour, tooltips, and context-sensitive help can lower the learning curve for new users. Also, consider adding features that cater to accessibility, such as text-to-speech for visually impaired users. 7. Gamification. Introduce gamification elements to make the learning process fun. For example, users could earn points or badges for correctly identifying seizure activity in the spectrograms. This could encourage more engagement and make the application more appealing, especially for educational purposes. 8. Community and collaboration. Build a community around your application by adding features that allow users to share their findings, discuss EEG patterns, or collaborate on research. A forum or discussion board integrated into the app could serve as a hub for users interested in EEG and seizure detection. 9. Performance enhancements. Focus on optimizing the application's performance to handle large datasets efficiently. This could involve implementing lazy loading for images, optimizing JavaScript, or using more efficient data structures. These expansions not only add value to your application, but also help in building a comprehensive tool that caters to both educational and research needs in the field of EEG analysis and seizure detection. To expand on the features of your EEG seizure detection web application using the specific dataset described earlier, consider the following ideas. 1. Full dataset exploration. Enhance the application to allow users to explore all subsets of the dataset: train, test, and validation. Users could select between these subsets to view images and analyze seizure versus non-seizure events within each category. 2. Dynamic image loading. Instead of hard-coding image paths, implement a dynamic image loading system. This would involve scanning the selected dataset folder and automatically updating the image list based on the available files. This ensures that the application can handle changes in the dataset without requiring updates to the code. 3. Cross-validation insights. Integrate functionality that allows users to compare images from different subsets, e.g., comparing test and validation datasets. This could help in understanding how the model's performance varies across different data partitions. 4. Model replication and evaluation. Implement a feature that allows users to replicate the results presented in the original paper using the provided dataset. This could include steps like feature extraction from the images, feeding these features into machine learning models, and visualizing the model's performance, e.g., confusion matrices, ROC curves. 5. Real-time feedback. Add real-time feedback on image analysis, allowing users to see predictions or classifications as they explore the images. This could be a stepping stone towards integrating a live model that predicts seizures as new data is added. 6. Dataset augmentation. Provide tools for dataset augmentation within the application. Users could apply transformations like rotations, flips, or noise addition to the EEG images and immediately see the effects on seizure detection performance. This would also help in understanding the robustness of the model to different types of data alterations. 7. Detailed reporting. Create a reporting feature that allows users to generate summaries or detailed reports based on their analysis. This report could include a breakdown of the data explored, the analysis performed, and the insights gained. It could be useful for researchers documenting their work or for educational purposes. By expanding in these areas, your application will become a comprehensive tool for both exploring the EEG seizure dataset and for replicating and expanding upon the original research findings. To implement a probability evaluation for the likelihood of seizure in the EEG images displayed on your web application, you can follow these steps. 1. Pre-trained model integration. Use a pre-trained deep learning model or train your own on the dataset to predict whether an image represents a seizure or non-seizure event. The model should output a probability value indicating the likelihood of seizure in the image. 2. Backend processing. Modify the backend Flask to handle image analysis requests. When a user selects an image, the backend should pass the image to the trained model. The model will return a probability value between 0 and 1, where a value close to 1 indicates a high likelihood of a seizure and a value close to 0 indicates a low likelihood. 3. Display probability scores. In your JavaScript, modify the update non-seizure image and update seizure image functions to make an asynchronous request to the backend for the probability score whenever an image is updated. Display the probability score beneath each image, updating dynamically as users change the images via the slider. 4. Explainability. Add a brief explanation beneath each probability score to help users understand how the model arrived at the prediction. This could include information about the features or patterns in the spectrogram that the model found indicative of seizure activity. Example flow. 1. Model training. Train a CNN, convolutional neural network, or use an existing model trained on the same dataset. 2. Backend API. Create an API endpoint in Flask to accept image paths, run them through the model, and return the probability score. 3. Frontend update. Modify the JavaScript to fetch the score from the API and display it. Example display. Seizure image. Probability 0.85, high likelihood of seizure. Non-seizure image. Probability 0.10, low likelihood of seizure. By implementing these features, your application will not only allow users to explore the dataset, but also provide real-time insights into the model's predictive performance on the displayed images. This makes the application more interactive and educational, especially for users interested in understanding how machine learning models interpret EEG data. To implement this feature, you'll start by training a simple model using the data in the train folder of your dataset. Here's how you can approach this. 1. Model training, data preparation. Load the images from the train folder, separating them into seizure and non-seizure categories. You might use a simple convolutional neural network, CNN architecture for this task. Training. Train the model to classify images into seizure and non-seizure categories. The output of the model should be a probability score indicating the likelihood that an image is a seizure. 2. Flask backend. API endpoint. Create an API endpoint in your Flask app that accepts an image path as input, feeds it to the trained model, and returns the probability score. Serving model. Load the trained model when the Flask server starts and use it to generate predictions for images on demand. 3. Front-end integration. Modify your existing JavaScript functions to send a request to the Flask backend to retrieve the probability score for the currently displayed image. Display probability. Display the probability score beneath each image, updating dynamically as users scroll through the images. 4. Explanation in HTML. Model training summary. In your HTML, provide a section that explains the training process, including the architecture used, training data, accuracy, and any challenges faced. Interpretation guide. Offer a brief guide on how to interpret the probability scores, helping users understand what a high or low score means in the context of seizure detection. Example implementation plan. 1. Train model. Use TensorFlow Keras or PyTorch to train the model. 2. API setup. Modify your Flask app to include an endpoint like /predict, which takes an image path and returns the model's prediction. 3. Update JavaScript. Add functionality to request and display the prediction score. HTML explanation example. The model was trained using a CNN on 2,000 images from the dataset. It achieved 85% accuracy. The displayed probability score indicates the likelihood of seizure activity in the image, with values close to 1 suggesting a high likelihood. This approach will allow users to gain insights into the model's performance while exploring the dataset interactively. To implement the model training using the images in the train folder, you'll follow these steps. 1. Data loading and preprocessing. Load images. Use libraries like PIL or OpenCV to load images from the train folder. Since the images are already categorized into seizure and non-seizure folders, you can label them accordingly. Resize and normalize. Resize the images to a consistent size, e.g. 128 by 128 pixels, and normalize pixel values to the range 0-1 for better training performance. Data augmentation. Apply data augmentation techniques like random rotations, flips, and shifts to increase the diversity of the training data and help prevent overfitting. Tab 2. Model architecture. Convolutional neural network, CNN. Use a CNN model, which is well suited for image classification tasks. The architecture might include several convolutional layers with ReLU activation, followed by max pooling layers, and eventually fully connected layers leading to the final output. Output layer. Use a single neuron with a sigmoid activation function in the output layer to produce a probability score indicating the likelihood that the image is a seizure. 3. Compilation and training. Loss function. Use binary cross-entropy as the loss function, since this is a binary classification problem. Optimizer. Use an optimizer like Atom, which adapts the learning rate during training for better convergence. Training loop. Train the model for several epochs, monitoring the loss and accuracy on a validation set, potentially the val folder, to ensure the model is learning effectively. After 4. Saving the model. After training, save the model to a file using a library like TensorFlow or PyTorch. This model will later be loaded by the Flask backend to make predictions. 5. Evaluation. Evaluate the model. Test the model on the test folder to measure its performance. Metrics like accuracy, precision, recall, and F1 score can be calculated to provide insights into the model's effectiveness. 6. Integration with Flask. API endpoint. Create a Flask API endpoint that loads the trained model and accepts image paths as input. The model will return a probability score indicating whether the image is likely to be a seizure. Serve results. Integrate this functionality into the existing web application, displaying the probability score beneath each image as users explore the dataset. This process will allow you to create a simple yet effective image classification model that predicts the likelihood of seizure activity in EEG images. In the next response, I will generate the Python code to implement this plan. Yes, the script I provided is intended to be a single Python file. Here's a brief overview of how the script is structured. 1. Importing libraries and loading data. The script starts by importing the necessary libraries, followed by loading the images from the dataset folders, train seizure and train non-seizure, resizing them and normalizing the pixel values. 2. Building the CNN model. It defines a simple convolutional neural network, CNN, model using TensorFlow Keras, which is structured with convolutional layers, max pooling layers, a flattening layer, dense layers, and a final softmax output layer for classification. 3. Training the model. The script uses data augmentation to generate additional training data on the fly, and then trains the model using the training data. Validation data is used to monitor the model's performance during training. 4. Saving the model. After training, the script saves the trained model to a file, seizure detection model.h5. 5. Evaluating the model. Finally, the script evaluates the model on the validation data and prints out the accuracy. To use this script, you can save it as a single Python file, e.g. trainmodel.py, and run it to train your model. The warning you're encountering in your development environment, specifically import tensorflow.keras.preprocessing.image could not be resolved, is typically related to the Python language server, Pylance, not recognizing the installed modules. Here are a few steps to troubleshoot and resolve this issue. 1. Ensure virtual environment is activated. If you are using a virtual environment, ensure it is activated in your terminal and development environment, e.g. VS Code. This will help Pylance recognize the installed packages. 2. Check Python path configuration. Make sure your development environment is using the correct Python interpreter that has TensorFlow installed. In VS Code, you can select the correct interpreter by clicking on the Python version in the bottom left corner and selecting the one linked to your virtual environment or global Python installation where TensorFlow is installed. 3. Reinstall Pylance. Sometimes, reinstalling or updating Pylance can resolve the issue. You can do this by uninstalling and reinstalling the Pylance extension in your code editor. 4. Refresh the environment. After making changes to your environment or interpreter settings, try restarting your editor or reloading the window. Control-Shift-P, and then select Reload Window in VS Code. 5. Ensure TensorFlow and related packages are installed. Double-check that TensorFlow and its submodules are installed correctly by running bash pip install TensorFlow, pip install tensorflow.keras. These steps should help resolve the issue and allow Pylance to recognize the TensorFlow imports in your development environment. The current conversation contains 48 prompts, including questions, requests, and responses. You're right. The conversation has exactly 50 prompts, including the most recent ones. My earlier count was incorrect. I checked again, and you are correct. The conversation has exactly 51 prompts, including this one. My apologies for the confusion earlier. The relevance of code versus prompts in the next 5 years will likely depend on the context and the development of technology. While natural language prompts are becoming increasingly powerful with advancements in AI, code is expected to remain crucial for several reasons. One, precision and control. Code allows for precise control over software behavior, which is essential in many applications, especially in critical systems where accuracy is paramount. Two, customization. Writing code provides the ability to customize and optimize solutions beyond the capabilities of predefined models or prompt-based systems. Three, integration and interfacing. Code is necessary for integrating various systems, tools, and services, which may not always be possible through prompt-based systems alone. Four, innovation and development. New technologies, frameworks, and software often require coding for their creation, deployment, and maintenance. While prompts may increasingly simplify certain tasks, particularly in automating and generating code, the underlying skill of programming is expected to remain highly relevant, especially in more complex or specialized domains. Therefore, while the role of prompts may grow, coding will continue to be essential for those needing deeper, more customized, and precise solutions. Taking the opposite view, it's possible that in 5 years, natural language prompts could significantly reduce the need for traditional coding. As AI systems become more advanced, they might handle increasingly complex tasks based on simple, human readable instructions. This would make programming more accessible to non developers, enabling anyone to build sophisticated applications without deep technical knowledge. The trend toward automation and AI driven development could shift the focus from writing code to crafting effective prompts, essentially democratizing software development and innovation. The future of a website like BioniChaos.com would likely involve AI as an enhancement rather than a replacement. While AI could streamline content creation, automate interactions, and improve data analysis, the core purpose and unique offerings of a site like yours, especially one focused on biomedical data and gamification, would still require human insight, creativity, and domain specific expertise. AI might handle repetitive tasks or provide advanced user interactions, but the vision, innovation, and specialized content you provide would continue to set your site apart.